Annenberg Media.
A volcanic eruption is one of the most awe-inspiring sights in all of nature. But whether an eruption is sudden and explosive, such as Mount St. Helens, or more subdued, like the eruptions of Kilauea in Hawaii, volcanic activity is not an unusual event. Volcanic eruptions are the pulse of geologic activity in the Earth's interior. They graphically demonstrate that geologic processes inside the Earth can have a direct impact here on the surface. The lava that's produced during a volcanic eruption is, of course, rock that melted somewhere beneath the volcano. Rock melts in a variety of geologic settings in the crust and upper mantle of the Earth, depending on the temperature and pressure conditions and on the composition and water content of the rocks. But lava represents only a tiny proportion of the magma that forms within the Earth. Most of this magma either seeps into voids and fractures within rocks of the Earth's crust, or it rises and intrudes into the cooler rocks above as enormous globs that require thousands or even millions of years to cool. In fact, most of the rock of this planet was formed from the slow cooling and crystallization of magma deep underground. This is known as intrusive igneous rock.
The study of igneous rocks began in the 1780s, when Scotsman James Hutton became embroiled in a controversy with another influential geologist, Abraham Werner. Werner believed that the Earth was once covered entirely by a great ocean, from which all rocks formed, starting with granite. Hutton disagreed. In exploring the highlands of Scotland, Hutton observed veins of granitic rock slicing across sedimentary strata. He reasoned that the granite must have been injected into the strata as a molten liquid and not been precipitated from a primordial sea. He made a link between granites formed at depth and the quickly cooling deposits of erupting volcanoes. Both are products of molten liquid, or magma, from Earth's interior. Thanks to Hutton, geologists recognized a new class of rocks called igneous, literally fire-formed rocks.
Some of the original heat that results in the formation of magma comes from the original formation of the Earth. As the materials came together that formed the Earth, they produced an enormous amount of compression. Now that was some 4.5 billion years ago, but some of that heat still remains in the interior of the Earth. Another source is from radioactive isotopes. Potassium, thorium, and uranium have all contributed as a result of radioactive decay to heating of the Earth, particularly in the earlier history of the Earth when these isotopes were more abundant. Now there's another contribution that comes from the tidal effects of the sun and the moon. As a result of these tides, the Earth is being constantly squeezed and flexed, and that tends to build up some heat in the Earth's interior as well.
The ascent of magma is a process called intrusion. If the magma cools underground, it forms an intrusive, sometimes called plutonic igneous rock. If it erupts at the surface, the igneous rock is called extrusive, or volcanic. James Hutton studied granite because it is among the common plutonic rocks of Scotland. But worldwide, there are in fact many types of plutonic rocks. Those that contain abundant iron and magnesium are called mafic rocks by geologists. Gabbro is an example. Felsic rocks, such as granite, contain abundant silica and alumina. Finally, many igneous rocks are essentially mixtures of mafic and felsic compositions. These are known as the intermediate igneous rocks. Diorite is one of the most abundant examples. Each of these plutonic rocks has a compositionally identical counterpart in volcanic rocks. But although they may be made of exactly the same material, their textures are very different. This can only be due to the fact that each cools and hardens under different conditions. Laboratory studies indicate that if the molten rock cools too quickly, crystals are unable to form, since the individual atoms in the melt don't have enough time to build crystal lattices. If the molten rock cools slowly, however, crystals will ultimately form throughout the magma. And the more slowly the magma cools, the larger the crystals will grow.
This dike formed when a hot andesitic magma welled up into a fracture in this gneiss. As the magma cooled, it transferred heat into the surrounding gneiss. Heat transfer was, of course, more rapid here at the contact, resulting in the gneiss being cooked by the magma heat. Because crystal size in igneous rocks is a good indicator of relative cooling rate, we can also see that the magma itself cooled more quickly at the contact. The smaller crystals here at the contact tell us that the magma cooled more quickly there than here at the center, where the crystals are somewhat larger.
Based upon texture, geologists infer that granites crystallize from magma cooling slowly deep underground. In contrast, rhyolites form from magma that cools slowly at first, allowing a small amount of the larger crystals called phenocrysts to develop. Then it cools quickly as a result of an eruption, stopping crystal growth altogether.
Textures that result in the crystallization of those minerals tells us about the conditions under which that rock formed. Some rocks have very large crystals that are easily visible to the naked eye, and we call that a phaneritic texture. Your everyday granite has a phaneritic texture, and that shows that that rock had to crystallize at some depth, several kilometers down in the Earth's crust. That rock represents a different time, and it's exposed now at the surface only due to later tectonic activity. Other rocks, other igneous rocks, crystallize near the surface. Volcanic rocks, for example, record a very rapid crystallization of the same kind of magma. But as the crystallization becomes more rapid, the crystals are forced to be smaller and smaller, becoming eventually aphanitic or invisible to the eye. Or even faster, the minerals don't have time to grow. And the result is volcanic glass, which we call obsidian. So we're learning to read textures from the rock, and we learn the conditions under which it forms.
By studying the crystal textures of igneous rocks, geologists have discovered that not all minerals form from a magma at the same time and temperature. Rather, magma crystallizes one or two mineral types at a time. The early forming crystals, those that can withstand higher temperatures, such as plagioclase or olivine, preserve symmetrical shapes that could only have resulted from the crystal formation taking place in a liquid. Later forming crystals, such as potassium feldspar and quartz, exhibit irregular shapes, indicating that they crystallized last, from small compartments of liquid confined in the spaces remaining between the early forming crystals. Lab work by Norman Bowen and other experimentalists has given us precise information about how magma crystallizes. Bowen called the sequence of mineral crystallization in magma a reaction series. This is because as magma cools, early forming minerals may react with the magma to form new minerals at lower temperatures. Some minerals react continuously with the magma and so are constantly undergoing change. Others react discontinuously, that is, only at certain specific temperatures.
The first minerals to crystallize are the calcium plagioclases, which would crystallize up about 1100, little more than 1100 degrees Celsius. Along with the calcic plagioclases, we'd expect to find crystallization of minerals like olivine. But as the temperature falls, different minerals begin to crystallize. In fact, some of the earlier minerals begin to convert into some of the minerals that crystallize at lower temperatures. And in the discontinuous series, we see olivine being dominated then and overtaken by pyroxene, pyroxene being changed into hornblende, hornblende into biotite. And there's a conversion, usually just a pair of minerals as we go to lower and lower temperatures. The low temperature minerals in Bowen's reaction series consist also of plagioclases. The continuous series changes from the calcium-rich plagioclase to the sodium-rich plagioclases. As we get down to temperatures of 800, 700 degrees Celsius, we have more sodic-rich plagioclases. We have minerals like K-feldspars, biotite, muscovite, and quartz crystallizing. These are the more felsic constituents in Bowen's reaction series.
The actual temperatures at which magma forms or crystallizes are influenced greatly by its water content. In general, the greater the water content, the lower the temperatures. By showing that magma crystallizes in a piecemeal fashion, Bowen provided an explanation for why plutonic rocks contain so many types of crystals and volcanoes so few. But Bowen's work has other important implications. It suggests that different kinds of igneous rocks can form from a single parent magma.
Bowen developed this series in response to the idea of what was the origin, the question, what is the origin of granite? He felt that all magmas originally started out as basaltic material, but through a process of differentiation, the magma evolved and changed. The early crystallizing materials, the materials that would crystallize at higher temperature, would tend to settle out or become separated in some way from the magma. This process is called differentiation, and it demonstrates how a magma might evolve so that you can change from what was originally a mafic magma into a felsic magma consisting of the lower melting minerals.
Geologists find evidence of differentiation preserved in many plutonic rocks. For example, some intrusions are layered due to settling out of early forming mafic minerals. As these minerals left the upper part of the magma body, only felsic minerals were left to crystallize there. At volcanoes, the composition of lava and ash may change in time, reflecting differentiation in the magma underneath.
The effect of cooling rate, water content, and magma composition on the resulting texture of intrusive igneous rocks can be investigated in a more complete and quantitative way using laboratory experiments. But a lab alone cannot recreate the geologic processes that cause a magma to form. These processes operate deep within the Earth's interior, and they are usually tied to tectonic processes and the movement of plates.
Igneous activity is directly related to plate tectonics. Ocean ridges, zones of spreading in the Earth's oceans is due to the upwelling of molten magma derived from partial melting in the mantle. And in melting mantle, the result is a magma that will crystallize to form basalt. And that's why basalt is the dominant rock type of ocean ridges, of ocean islands, and ocean crust. At subduction zones, that ocean crust, made of basalt again, is subducted, taken back down the Earth's mantle, and is heated. It then is partial melted, and magma rising from that partial melt rises to form the great volcanoes above the rim of fire.
Particular types of magma are associated with specific types of plate boundaries.
Plate tectonic theory explains why we have magmas on the seafloor, which are very different from magmas that form on continents. The magmas on the seafloor are enriched in iron and magnesium, tending to be on the basaltic side of the scale, higher temperature minerals in accordance with Bowen's reaction series. In subduction zones, relatively cool, wet rocks on the seafloor, seafloor lithosphere, are subducted under continents, and because of the presence of so much water, melting begins at a low temperature, thus partial melting takes place, and we tend to get rocks that are higher in silica associated with subduction zones, hence andesite volcanoes in South America, rather than the basaltic type rocks in the mid-oceanic ridges.
At convergent plate boundaries, andesite and its plutonic equivalent diorite are among the most common igneous rocks. But geologists are uncertain of how their parent magma forms.
We think that much of the magma develops as a result of melting of basalt from the upper part of the descending lithospheric plate. There may also be components that are derived from the marine sediments that may also be carried down. These marine sediments may have interstitial water that can also contribute to and become dissolved in the magma. There may be substantial amounts of serpentine that are being brought down with the basalt. These are hydrated minerals and could also contribute water. Now, the presence of water is significant because it helps to bring about a fluxing of the remaining amount of material. It lowers the melting point, and it helps in the formation of magma. Now, as this magma moves up towards the surface, is it basaltic in composition? Is it more felsic? We aren't completely certain of the nature of the magma. As this magma moves up towards the surface, it encounters the base of the Earth's crust, mainly made up of felsic constituents. These are lower melting material. As we look at Bowen's reaction series, we see that these minerals from the continental crust are really the low melting materials. So they are very likely to become incorporated into the magma.
In fact, partial melting of continental crust, mantle, and subducting slabs probably all contribute to the formation of andesite and diorite. But these aren't the only igneous rocks that form at convergent plate boundaries. Many other types also occur. Partial melting in the mantle, triggered by upwelling associated with subduction, will form basaltic magma. This magma may collect, cool, and harden at the base of the crust.
In some cases, though, the magma may move rapidly up towards the surface, still a basaltic composition, and erupt as a basaltic lava at the Earth's surface. If it's held for some time within the Earth's crust, assimilation may take place, where large amounts of the crust may be melted and incorporated into this magma so that it becomes higher in felsic constituents. And these felsic constituents then increase the viscosity so that the magma doesn't so easily move up to the surface to erupt as a volcano, but instead it lodges itself within the crust of the Earth as a pluton.
Plutons, huge masses of igneous rock, also form when continental crust and sediment are partially melted by the heat of rising mafic magmas. The molten continental material cools to form one of the most characteristic rocks of convergent plate boundaries, granite. Magma rises from the Earth's interior because it is buoyant, that is, less dense than the rock material surrounding it. It ascends in several ways. At divergent plate boundaries, magma simply fills up the spaces opened as the crust is pulled apart. By contrast, at convergent plate boundaries, rock enclosing a magma body may be pushed aside as the magma passes through it. Or the magma may fracture the overlying country rock through a process called stoping. Bits of fractured country rock sink into the magma chamber, where they may be preserved upon cooling in the form of fragments called xenoliths. In part, magma may even melt its way through the crust, increasing in volume and changing in composition. Once formed, igneous intrusions are classified according to their geometric shapes and overall size. Small, common intrusions possessing sheet-like shapes that cut across the bedding or fabric of pre-existing rocks are called dikes. Sills are related to dikes, but instead of cutting across strata as dikes do, sills intrude between layers, forming sheets parallel to the strata. A laccolith is a shallow sill-like structure that bulges upwards in its central portion, often causing a hump or gentle rise in the overlying crust. The largest intrusions, typically having the shape of spheroidal blobs, are the plutons. These range from masses called stocks, which crop out over areas tens of square kilometers, to gigantic intrusions exposed over hundreds of square kilometers. Geologists call these huge plutons batholiths. Plutons often rise in groups, so a batholith can, in fact, be composed of many plutons merged together.
Watching a lava lamp can give us a good deal of insight into the way a batholith forms. When rocks melt in the lithosphere of the Earth, the magma begins to rise because it's less dense than the surrounding rock, just as these buoyant blobs rise through the surrounding oil when the base of the lamp is heated. As the bubbles of magma make their way toward the surface of the Earth, they begin to expand and pack together, coalescing and cooling into a huge mass of plutonic igneous rock. A composite igneous intrusion like this can be immense, encompassing tens, or in the case of a batholith, several hundred individual plutons. When erosion eventually strips away the several kilometers of rock covering the batholith, the mass of plutonic rock remains as an elongate mountain range. Plutonic rocks are composed of a tightly intergrown mass of crystals, which is usually more resistant to weathering than the sedimentary and metamorphic rocks which surround the magmatic intrusion. Geologists use batholiths to try to understand the tectonic history of the Earth's crust. The Sierra Nevada batholith here in eastern California is an excellent example. The hundreds of individual plutons which make up this batholithic mountain range represent a series of magmatic intrusions that began about 200 million years ago and continued over the next 120 million years. Most of this plutonic rock is chemically very similar to andesite, a volcanic rock that's found forming in continental volcanic arcs, such as the Andes. These arcs exist because oceanic crust is being subducted beneath the edge of a continent. Partial melting of the downgoing rocks generates the andesitic magma, which rises in buoyant plumes to feed the volcanoes or to become part of the batholith below. So the overall structure and composition of the Sierran plutonic rocks tells us that this is a deeply eroded magmatic arc, which formed along an ancient subduction margin.
The study of ancient igneous rocks has not only provided a wealth of information concerning past tectonic processes, it has revealed much about the evolution of Earth's crust. One ancient type of igneous rock is komatiite, a rare class of basalt formed from much higher temperatures than the hottest basalt lavas known today. Komateites suggest the Earth once had a much warmer interior. Anorthosite is another kind of rock that is relatively rare on Earth and almost entirely embedded in ancient plutonic belts cutting across the older portions of the continents. Anorthosite may be rare on Earth, but it is the primary type of rock found in the highlands of our nearest neighbor in space, the Moon.
When the astronauts came back from the Moon, they brought back samples of a kind of rock called anorthosite. Apparently it's very common on the surface of the Moon, but it tends to be relatively rare here on Earth. I have an example of an anorthosite here. This one comes from the San Gabriel Mountains, and it seems to represent a body of rock that was formed at great depth in the interior of the Earth. It may have started out as a rock of basaltic composition, a magma of basaltic composition, but it was held at great depth for a long period of time, long enough that the crystals had an opportunity to grow very large. I don't know if you can see, but this is made up of extremely large crystals. It was evidently under tremendous pressure at that depth as well, and so this magma has undergone an extreme amount of differentiation. That is to say, there was a separation of the crystals from the melt. Apparently these crystals settled to the bottom of the chamber, where they became almost purely made up of this one kind of crystal. In this case, it's a calcium-rich plagioclase, and the kind of rock made almost exclusively of this plagioclase is called, as I say, anorthosite. I have another example here, also from the San Gabriel Mountains, that gives us an idea of how this differentiation may have proceeded. The crystals grew large. We can almost imagine the magma surrounding them in this area here. and the crystals settling down. These are single large crystals. You can tell by their uniform shape and the straight sides. Large crystals growing in what was molten rock surrounding it. And these crystals then settled to the bottom of the chamber. This sample is well over 1 billion years old, and all of the other known anorthosites are very old as well.
The presence of very ancient anorthosite, both on Earth and the Moon, suggests that these worlds may once have been more similar in composition. But Earth's interior, still geologically alive, has allowed our planet to continue evolving, while the Moon, now geologically dead, remains the same. Indeed, the formation, ascent, and cooling of magma is one of the most significant agents of change in Earth's vast interior.
Throughout geologic time, the great heat generated within the interior of the Earth has caused rocks to melt. Most of the Earth is composed of intrusive igneous rocks. The continents are largely masses of granitic rock beneath a thin blanket of soil and sediment. Oceanic crust is mostly gabbro, coated with basalt and mud. Even the rocks of the Earth's mantle were formed from the slow cooling of ultramafic magmas. And so far, evidence from the interior planets of our solar system indicate that they too formed in a similar way. Geologists can't study igneous intrusions directly, but by analyzing the minerals within these rocks and mapping their physical relationships, Earth scientists are gaining an intimate understanding of the evolution of the lithosphere. Research into intrusive igneous processes is now more important and interesting than ever. For example, it's used in determining the location of metallic ores, precious metals, and gems, for interpreting the complexities of plate tectonics, and in studying the history of other planets similar to our own. Intrusive igneous rocks remind us that a great deal of geologic activity takes place in a vast, unseen arena. There, in the Earth's interior, magma continues to form and move about and crystallize, setting the stage for the growth of the ocean basins, the continents, and the mountain ranges of the future.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.